Science narrative analysis, potential eruption of Yellowstone. Yellowstone is not an ordinary volcano. It is a supervolcano, one of the most powerful natural systems on Earth. Unlike the towering stratovolcanoes such as Mount Fuji in Japan or Mount Etna in Italy, Yellowstone hides its volcanic might beneath a vast caldera, a depression that spans about 45 by 75 kilometers. This caldera was created by cataclysmic eruptions in the past, the most recent occurring approximately 640,000 years ago, which blanketed much of North America in ash and altered the global climate. Earthquakes, Yellowstone's language. At the heart of Yellowstone's monitoring lies the study of earthquakes. Each year, Yellowstone experiences 1,500 to 3,000 earthquakes, most of them too small to be felt by humans. These tremors are not random. Many occur in swarms, where dozens or even hundreds of small quakes happen within days or weeks. Unlike destructive, tectonic quakes, these swarms often indicate the movement of magma, gases, and hydrothermal fluids beneath the surface. While most swarms subside without incident, their importance lies in patterns. For example, a sudden increase in magnitude or frequency could hint that magma is migrating closer to the surface. Scientists look for changes in depth, duration, and location of seismic events to separate normal background activity from potential precursors to eruption. Beyond local tectonics, a window into magma systems. Yellowstone sits atop a hotspot, ACED, mantle plume, that brings heat and magma from deep within the Earth. Unlike tectonic plate boundaries, hotspots remain relatively stationary while plates move over them. Earthquake studies here, therefore, are not just about tectonic shifts. They are a way to peer inside the hidden magma chambers. Recent geophysical imaging has revealed that Yellowstone contains a dual magma system. A shallower reservoir of mostly solid rock with pockets of molten material, a deeper chamber connected to the mantle plume with even larger magma reserves. The constant interplay between these chambers, fluids, and overlying rock explains much of the seismicity observed. Monitoring the giant. The Yellowstone Volcano Observatory, YVO, a collaboration between the U.S. Geological Survey, universities, and the National Park Service, acts as a sentinel. Using an array of seismometers, GPS stations, and satellite data, YVO scientists track the subtle rise and fall of the ground, known as ground deformation, as well as seismic vibrations and gas emissions. Seismic monitoring identifies earthquake swarms and patterns. GPS and INSAR, satellite radar, detects uplift or subsidence of the caldera floor, sometimes rising by several centimeters per year. Gas emissions measures carbon dioxide and sulfur dioxide levels, which can signal increased magmatic activity. These tools create a comprehensive picture, allowing scientists to distinguish between normal hydrothermal activity, such as geysers and hot springs, and deeper volcanic unrest. Global implications of a supereruption. Although the chance of a Yellowstone supereruption in our lifetimes is extremely low, The consequences would be global. Past eruptions expelled thousands of cubic kilometers of material, compared to the much smaller 1980 Mount St. Helens eruption. The result would be massive ashfall across North America, crippling agriculture and infrastructure, climate disruption, as volcanic gases and ash particles block sunlight, leading to temporary global cooling, economic and societal impacts worldwide due to food shortages, transportation collapse, and environmental stress. Fortunately, smaller eruptions, such as hydrothermal explosions or localized lava flows, are far more likely than a catastrophic super eruption. These smaller events, while dangerous on a local scale, would not devastate the planet. Comparisons. Lessons from other supervolcanoes. Yellowstone is not alone in its potential power. Studying other supervolcanoes provides important context. Toba, Indonesia, 74,000 years ago. Its eruption is believed to have nearly caused a volcanic winter, drastically reducing human populations. Taupo, New Zealand, about 6,500 years ago, produced one of the largest eruptions of the last 70,000 years, leaving geological records across the Pacific. Campi Flegrei, Italy, still active today with frequent seismic unrest beneath Naples, reminding us that supervolcano hazards exist worldwide. By comparing seismic signals and eruption histories, scientists refine their models of how magma systems evolve before major eruptions. Conclusion: earthquakes as warnings, science as shield. Yellowstones. Earthquakes are more than just rumblings beneath a national park. They are messages from Earth's interior. Each tremor adds a piece to the puzzle of how magma moves, how pressure builds, and how a supervolcano breathes. While the probability of a super eruption in the foreseeable future remains very small, the science of monitoring ensures that humanity is better prepared than ever before. Earthquakes, ground shifts, and gas emissions are not just signs of danger, but tools of foresight. They remind us that Yellowstone, though slumbering, is alive, and that understanding its rhythms is essential for safeguarding the future.